So as we said again, this is chapter 16, the concept of logic programming language. As also we mentioned, there's a lot of theory here, and we shall go through them one at a time. So for example, what is a logic program? I'll use the example of SQL, sequential query language. Now, if I'm writing a query in a database system, well, I don't need any algorithm or all I have to do, write my select statement, select or select student name, city from the table, student table. Then we have where student from New York or the town is New York, any criteria you have. Then you run the query, you get the result. Same thing with a logic program. So in logic program, especially I would say the prologue, we have to have the facts. The facts always is true. We have to have the facts. We also have to have, I'll say the rules. The rules also very important. And we call it the clauses, etc. So I have the rules that if it's yellow or if the light is red, you stop your car. If it's yellow, you yield, etc. So next time I'm going to, it's like writing a query now. I will set a query that, okay, at this time, the light is this or this, what should be the outcome? And it will give us the outcome. So that's why it's called declarative, kind of exactly like writing a query. I would say writing a query. So that's a logic. And also we have what we call the logical inference. So this is where it's trying to find the correct result, inferential concept. So here we say again, the logic program is declarative program. And what is a declarative program? There's again a definition. Basically, it's going to describe what is desired from a program, not how to, again, here we are not going to write no algorithm. There's no algorithm. So not how should be done. So here we say declarative language, statement of facts, and also propositions that must be satisfied. And I think the previous lecture, we went through what a proposition must be a simple sentences, or it can be a complex sentences, but it have to give us a specific result, whether true or false. So for example, stand up, I don't know, you may stand up or not. So that's not a proposition. So a proposition, so actually, let's start with that first. So for example, here we say, what is a proposition? What is facts, rules, actually, this is what we need. Compound term, I would say it's more or less like having two or more conditions or items. So to have a compound term, you can also use the connectives. I think we went through that, like and or, not is unary, and or implication by conditional. So let's see that they gave us example here. Example for a fact, of course, we all know always salmon cannot be anything than a fish. So that's a fact. So here we say a salmon is a fish. Or cat likes tuna. And this is a fact. A predicate, now from here we can see the predicate, which is the lowest unit. So fish and like. So a predicate is what? It's a function, all right? It's a function. But we also have a function. A regular function can be anything. But a predicate is a function that have to be what? True or false. True or false. So here, for example, a fish function, let me call it a fish function. It have to be either true or false. That's the only two options. And also the compound terms, we all understand what the meaning of compound. We have more than one unit or something. So here, for example, actually, this is very interesting. We'll see something like this in the prologue language. We use the variable x. Now we say cat like x. Oh, x is what? A fish. So x is fish. And the lowest unit, same as skin. The lowest unit is atoms. So here we have, again, from this example here, we have cat, salmon, tuna. Now we didn't say fish, because when we look here, fish is like, not like, fish is a function. So fish is predicates, fish and like. But the atoms here are the atoms. Then the rule can be any rule now. So what rule we have here? Let's see. We say, okay, cat eat x. Cat eat x. Why? Because cat like x. And what is x? X is a fish. So this would be a very nice rule here for us. So that's the whole concept for, I would say, for the whole course here, for this chapter. system. If we understand this concept, then I think it's very straightforward. So let me wait for a few seconds if any question. Okay, so we have one example. Here we say a horse is a mama. So these are our facts now. Human horse has no arms, human we have arms, etc. And now we can see at the so we can what is represented here is the same thing represented here. So this small, so everything here will be a proposition. A horse has no arms. You have to be true or false. So let's say, and also, so I can write this as this. Horse is what is this? Human is what is this? Then we say for all, mama have 4 legs and no arms, or 2 legs and 2 arms. So we say for all x belongs to this. There's a chance that x may have 4 legs, or x may not have no arms, or x has 2 legs, or the last section, x has 2. So human being, we have 2. Animal, most of the time they have 4. Example would be the ox. So this is the whole concept of, again, logic. Let me wait for a few seconds if it's okay. Yes, so let's keep going. So first we're going to start with what we call the first order predicate calculus. And I think this example gives us the whole idea. So here we say A implies to B, and also B implies to C. Okay, so that means if A to B and B to C, then A can go to C. So A implies to C. So that's what we mean the inference rule, ways of deriving or proving new statement from what a given set of statement. So the given set of statement they gave us here is A implies to B, and also B implies to C. So we were able to inference, and we came that, okay, if that's the case, then also A will be implied to C then, because both A and C, they are A to B, B to C. So A can go to C. So that's the example they gave us. And if no question, then the next we have, we saw from the example 1. So if now we are going to check, we know us. So I think the first will be true. Also have 4 legs. And the second one also is true. Human have 2 legs. And also the third one is true. Human have 2 arms. So basically, again, that's this can be derived again from the example that we saw, those statements. So they say theorem will be the statement derived from axioms. Axioms normally would describe, or I'll use the term axiomatic, that describe the construct. So here, for example, say a collection of statements is assumed to be axiom. So that will be basically the construct of the program, in this case, logic. And from them, a desired fact is derived by application of inference rule in some automated way, as we saw in, again, the previous slide. Yeah, so wait for a few seconds. If no question, now let's see the definition again one more time. So what is a logic programming language? What is a logic? And also the concept of query. So query and goals. And so as we said, logic is more or less like SQL. I have my facts, rules, everything. So I write a query. See if it will fire any of the rules concept. And previously, logic programming is very, very famous, but now I don't know if I would say it's famous. Because back in the 80s, early 90s, instead of developing data mining applications, what we develop? We develop expert system, because those days we don't have the data. So if I want to develop a model to predict disease A, I don't have a data set like today. I may get 10,000 data set of of patients that have disease A. I don't need an expert. But in those days, we don't have no data, so we're going to get what? An expert. The expert will be a doctor who specializes in disease A. And all we are going to do is to write all these rules. Again, normally in expert system, we call it knowledge base. So KB, you write all the rules, Most of the rules will be if then, if then, if then. And the same thing we are going to see in logic, the concept here. Most of the time we have what we call the head and headless, we're going to see everything. So that's the whole goal here, whatever query. So in this case, I have an expert system. My query will be, I have a new patient, and this is the diagnosis. If the color of his eye is yellow, the body temperature is more than 100, then you have a fever. So I have that as a query, put it in the system. If any of the rule apply, then it will fire it up. So we should understand, I think we already went through what is a proposition already, a logical statement that may or may not be true. Also, we say it consists of objects and also relationship of objects to, again, each other. Then the next section is the symbolic logic also. Okay, most of the items here are theory. As we said, mostly will be based on predicate calculus. So we say the particular form of symbolic logic used for logic programming again is the predicate calculus. For example, we saw fish, salmon. That's again the whole concept of a predicate. So we have what we call the first order predicate calculus, which is a way of what formally expressing the logical statement. Then, as we said, the definition for axiom also, the logical statement that are assumed to be true, or I would say the main construct to be true, and from which other true statements can be also get proved. And the rest here is just the definitions. So we should know what is a constant. So these are all the items that consist of, I would say, the prologue or logic program. I think the most important will be this, we should know connectives, which I think we went through. Most of the connectives here we are going to use will be only two, will be the end. This is blood pressure, the blood pressure is 100, and eye color red, and another thing in price to what? So that will be the input. So mostly we also sometimes we may use for it depends. Again, and or not an implication, and also equivalency. Equivalency is the same as what the by conditional. We saw the atoms, we may have constant values or variable like x, let's represent fish or something. And also the quantifiers. So this will be the operation that introduces the variables. And we may say this again in the language. So wait for a few seconds. A constant, same as any constant variable, maybe in the regular program. It can be a value or it can be a name. Predicate, we already saw it. It's a function. But we can see the definition now. A function that must be what? True or false. A function must be true or false. Then we have a regular function. It can be anything. So a function that returns non-Boolean values. A predicate will always return a Boolean value, either true or false. So this is the example again. I think we saw this example in the previous slide. What are the concepts of propositional or logic statement here? 0 is a natural number, 2 is a natural number. So all this again can either is true or false. And we can translate it to a predicate calculus. So natural become a function, or sorry, it become a predicate. And then we have the atoms or the constant values. So natural of 0 is a natural number, 2 is a natural number, etc. And here also we go through the same two, what is constant again, what is variable. Now, why do we see two definitions at the same time? Again, I intentionally put it. The previous one is from different source. The section here is from the textbook, so kind of sometimes put the two together, but to explain means the same thing, but just the way the sentences is. Also, we already saw what is atomic, lowest unit. So atomic proposition consists of compound terms. And what is a compound term? When we have two or more, so one element of a mathematical relation written like a mathematical function. But again, let's see examples straight here. Yeah, so these are some of the examples. For example, we have student John or John. This means John is a student. And we have another one set. Normally when we are reading, we read from left to right. So this is easy to read. And John is a student. But here we're going to say, we will not say this, we say this like this. So in this case, set like OX, X, and Nick like Windows, Jim like, again, Linus. And this will be, again, a compound term. So yes, a compound term composed of what? Two parts. The function symbol that names the relationship. And also other lists. So student is the main thing. Then the list of parameter will be either John, or the second one we have set, and also we have OSX. Okay, so if no question, so this is the textbook. Also, we already saw what is a factor already. So a factor always must be true. Like we saw the fish, salmon is always fish. We cannot say John is always a student. In this concept, we can say yes, but maybe it will graduate and it's not, but at that very moment, it's true. So fact will be a proposition that we always assume is true. It cannot be false. Then query will be the truth of proposition. That is, so query is what I want to find the result. So I'll query the system. If again, my query will be true or false, whatever I want to do. Again, we're going to see examples soon. And I think we went through all this. Negation, conjunction. So conjunction is and, disjunction or, equivalence, and also implication. Equivalence also sometimes we must say biconditional. So equivalence means A to B and B to A also. So it's go biconditional. What we will see a lot is the implication in a prologue language. So now we have to pay attention to the syntax. We can see what I'm trying to say is this is very perfect, which means A implies to B. So A, if A, then B. So this will be if condition. Now I will let this face this way. That means if B, then A. That's the consequent and the antecedent. So this will be mostly if then rules throughout. Then also we're going to see only I think discrete mathematics also, the quantifiers are only two, universal or existential. Universal means everything. So for example, the opposite or upside down A means all. So for example, the meaning is for all X, P is true. Or the down existential, sum. There is a value of X such that P is true, not all, but there is. So it will be sum. So I think that's only two quantifiers in discrete, universal or existential. Also, we have some proposition. I'll wait for a few seconds. I think this is like repeating what we did a little bit last week. So what is a proposition again? And the down, we said they are not Y, sit down, or variables. X can be any value. But if it's 1 plus 0, yes, I know true, 1. 0 plus 0, always false. But S plus 1 equal to 2, if S is 1, then it's true. But if S is 0, then it's false. So the variable section below, they are not propositions. Then how do we construct propositions? I think this is what we went through last week also, using, again, the connectives, negation, conjunction, disjunction, implication, biconditional. And we were able to come up with all the truth tables. Wait for a few seconds. So negation, we say what? It's more or less a complement. Complement true is false. Complement false is true. And conjunction will be like multiplication of products. So we have a true will be true, the rest will be false. Disjunction is all. We only get false if all of them, here we have only two inputs. If PQ is false, then it's false. Other than that, they are all true. Then we also talk about the exclusive or. We said if it's true, then it's false. If it's false, then it's false. It's only true if they are different, true, false, and false, true, give us true. Then we also saw the implication. It's only false if section is true, then it's false, or the antecedent and consequent, then that's where we have false. But if it's false and then it's true, we still get true. So we only get false if section is true, then section is false. So that's what they explained to us. So the whole concept of the implication is using the if-then rules. Again, if-then rules. So example again, if the moon is made of green cheese, then that will be the implication. Then I have more money than Bill Gates, etc. Also, this is another example given. And this is the biconditional, which means you have to go both sides. So biconditional is kind of opposite of exclusive or. We only get true if both sides is true or both sides is false. Exclusive or if both sides is true, both sides is false, we get false. And this is what we are going to, a unification and resolution. Those are the two things we are going to see in a prologue. So here we say resolution is an inference principle that allows inferred proposition to be computed from given proposition, which will be the query. So there's two ways we can do that, and we'll again hopefully see it soon. We can do the backward or forward way, which means you start with the goal and you look for the fat, or you start with fat and look for the goal. And the next terminology is what is unification, finding the values of variables in proposition that allow matching process to succeed. So it's like a pattern matching again, like we have the X maybe represent fish based on the sentences we have, etc. And also we have two types, which is the Krauses, the horn, we have the head and also headless. So the headed means single atomic proposition only on the left side. So we have the only if section, we don't have the then section. Then headless means we have empty left side that we use to again state a fact. Again, we're going to see, we're going to see examples soon. Then the last section on this slide is what is a declarative semantics. And as we all know, programming is, again, programming regularly is procedural. We have to write algorithm. But here we are talking about logic programming. It's not procedural, so non-procedural. Programs do not state now a result is to be computed, but rather the form of the result. So do not state how, I'll say how the result will be to compute the result. So that's the whole concept of, again, logic programming language. Now, if no question, then let's go straight to the second slide. Okay, so the second slide here, we shall go through the whole concept of prologue. Again, I'm using the slide straight from the book, so the book doesn't go detail about it, but again, just to get the idea of the whole concept. So the origin of a prologue is two different places, one in France and one in Edinburgh University. The book here used the Edinburgh one, so that's what they say here. The book uses the Edinburgh syntax of prologue. So far we know what is a term. It can be a constant, variable, or structure. And also, so prologue also may have a concept of list as a structure also. Then we already know what is a constant, an atom or integer. And also we know what is an atom with symbolic value of prologue in this case. So an atom can be values, letters, characters. So the example given here, string of letters, digit, underscore, beginning with a lower case letter. And also a string of printable ASCII characters also. So first we should know what is a variable and also what is an, so the keyword instantiation here is a little bit different from object-oriented programming. So here we are saying binding a variable to a value. They use the term instantiation of. And also a variable can be any string of letters, digits, underscore, etc. A structure normally look like a list also. So represent atomic proposition factor, which will be the parameter list. So wait for a few seconds if it's okay. I'll say variable is same as any variable, but the instantiation is kind of a little bit different. So when we say instantiation, logic programming, again, binding a variable to a value. Okay, so if no question now, let's say, okay, so this is our I think we got this idea already. So this will be our fact statement. And the first fact statement we have here, we say Shelley is a female. And also Bill is a male. And Bill father is Jake. So this will be, again, why is it headless? Because we don't have to the right side. This is only there. So in this case, we can say the female, male, father are the predicates, and the atoms are Shelley, Bill, etc. So this can be, again, a fact for us. So this fact always will be true. Bill is always a male. Again, Shelley is always a female. Then now we can come up with the sentences now. As we said earlier, we have the slide here will say antecedent on the right side, but we are assuming that maybe I'm standing like this. So this is my right. But when I'm looking at it, antecedent is my left side, but it's right. Let's assume it's right. So always the if section, this is explained to it. The if part is always the antecedent. So when they say right side, they mean I'm here, it's right. But if you face your computer, you may think it's left. Previously, I'm reading it kind of, I thought I have to change it to left and right. But later I say, let me leave it like that. So, but the main thing is that we see the if. So if antecedent, then consequent. So I would say most of the prologue is the rules, mostly rules, if then, if then, if then. So also we have conjunction. Conjunction here, we have a multiple term separated by logical end, or disjunction, or. But majority will be conjunction, as we said earlier, with implication. So if then is implication, if this, then whatever follow. So this will be the basic concept of the prologue. And let's see if we got some more example here. Also, this will be a rule. So this rule came from, we have the facts here. So as we saw in the previous slide, we can look at our facts to create a rule. So we have the facts here, Bill, father, Jake, Shelley, female. And now we came up with this rule. So this rule is true because what? If the Mary and Shelley are ancestors, that means Mary ancestor is Shelley, then one is a mother and one is a child. So this rule, this is based on the fact, because we must have the facts first before we construct the rule. So that's true. So Mary ancestor is Shelley, then that means Mary mother also. And also the second section, you can see what they said we can do. So in a prologue, the symbol is if. We have if then. So this will be if section, then we use this for then. We also have assignment operator. Let's say if we want to arrange that, we also have a arithmetic operator. We can do arithmetic operation with prologue, etc. But let's wait for a few seconds if it's okay. Now you can see, based on the rule, we can also use variables. So instead of saying Mary Shelley, maybe we may have different names. So let's say parent X. If X is a parent of Y, then X can be the mother of Y. So we represent them by using variables throughout. And also if father also is included. So wait for a few seconds. And also, this is what we have to, so this means N. Again, this is prologue now. This means N. Then semicolon is all. Semicolon is all. So this means this and this, based on this. So we have grandparents. So my child is grandparent. So we can see X and y, and so x will be the father, no, the ancestor. Then y, x born y, and z born y. So that means z grandparent is x, kind of that. If it's okay. Okay, so let's keep going then. Let's see more rules coming. So yeah, and now, okay, so now we have our rules, now we have our facts. The goal statement is what we do. So they say for theorem proving, theory is in the form of proposition that we want system to prove or disapprove. And that will be the goal statement. So a format, this is a headless one. Fred is a man. We may check. Or another one we have, X father is Mike. We can also check on that. And another example given here, to prove a goal is true, we must find a chain of inference rules or facts to follow. Here we say the goal is Q. So for example, if P2, then P1, then P3, then P2, then we may have as many rules all the way to, let's say, Q, then Pn. Then if we have any, again, query or anything we want to achieve, then we may see if any of these rules may fire out. So the process of proving a sub-goal called matching, satisfying, or resolution. I'll say matching, see if any of these rules again. Now, the approaches we can use, as we said earlier, we have the forward chaining, and also we have the backward chaining. So one, you're going to start from the goal and reach the fact. Or the opposite, I'll start from the fact to see if I'll reach the goal. So the matching is the process of proving a proposition, whether it's true or false. The proving will be a sub-goal, and that is called, proving a sub-goal, that is called satisfying the sub-goal. So two ways, as we said, bottom-up resolution. So forward chaining means I'll start with the fact going. So begin with the facts and the rules of database and attempt to reach your goal, if that will lead you to the goal. So again, that's why it's called forward. Now backward means I rather will go, I know the goal, and I'll see if the goal can reach the fact. So which we call the top-down resolution. Begin with a goal and attempt to do what? Find a sequence that will lead to the set of facts in the database system. And they say this works well with a small set of possible correct chain. Now, Prolog will use the backward. Prolog use the backward. So again, start with the goal and then see if we may find some sequence. And also maybe some of you know the depth first search and also breadth first search. So here we say when a goal has more than one sub-goal, we can either use the depth first search, which means we find one level at a time. So find a complete proof for first sub before working on others. So go by levels. Or breadth first search, work on all sub-goals in para also. Prolog use depth first search or depth first search, which can be done with fewer resources. Again, as we said earlier, when you look at the book doesn't go detailed much, but just to give us the idea about what is a logic program using a Prolog as an example. So the next will be the arithmetic operation. Again, we can perform all arithmetic operation. Like for example, here we have, now the is the equal sign. So that's the syntax. So we can have an integer variable, arithmetic. Each operator takes an arithmetic operation as right operand and a variable as left operand. So if I say A is B divided by 17 plus 16, it means we find a B divided by 17 plus 16, we assign it. I will use that sign, and let's say we say equal to A. So is again is and also that the reason why I didn't say assign, because we can see what they are saying here, almost the same as functional programming. So I cannot say sum is sum plus number. This is not assignment operator, it's equal. So yeah, so that's all we can say here. Let me wait for a few seconds if it's okay. Also, Prolog have recursive function. You can write your, but again, we only cover what the book told us to cover. We will not go. So this is a very good example for a factorial of a number. Again, we say the equal simply means comparison for identity when you use equal. So is something is equal to something. The one equal sign means I'm checking equality, like two equal sign for C++, Java, etc. So here we have a factorial n1. Here what we are trying to say is what? You see here, it doesn't look like a functional programming language. We are not even using the if-else statement. But what are we writing there? Who can tell us what is going on there? It's more or less like a base case, am I right? But in functional or Java, we have to write the algorithm. We have to say, okay, if n equal to 1, return 1, factorial. But here we are telling them the answer. So this is, I'll say recursion. Here we are saying that, okay, if the factorial n is 1, then the answer is what? 0. Or, if the factorial is 0, then so that's how we just writing the answer down. So that's why we say this is the, now you can also see the down one. We have product x, y, z. And now we say it's the same as saying z is what? S times y. So you multiply s and y, then you give the result to z. We give the result to z. Now we can see two examples. The second one will not work. Why? Because the order of it. So 3, 4, and good. I'll do its product. So I'll multiply 3 times 4 and I'll give the result to n. But when we come down, and this is the rule that we have. The rule doesn't work here because we don't know the value of y. And they say we should put the result in z, but we have 12. So you have to match like this, have to be with this. So again, that's the whole concept. So you can see here, we are not doing, I keep repeating, but we are not doing no algorithm. We have the result there. We have to state our rules. So this will be my rule. If I want to find a product of two numbers, put the two first values, and then the third variable will be the result. That's it. That's the fact. Unless I can change this rule saying that, okay, put the result in y, and the first two values will be x and z. If we have that rule and we said it, okay, here will be y is x and z, then this will work in order. They have to be in order. Now let's see some functions. A lot of we have some facts. Facts. So we can see a speed. The Ford, let's say Ford car go up to 100, Chevy go 105, Dodge 95, Volvo 80, etc., all the way down, and their time also is down. So these are all facts, and we came with a rule. So that's the interesting thing about, actually this is all about logic programming. So we get the facts, from the fact we build a rule. Then now we query. I want the result. I want the distance for Chevy. So how do I know the distance? Well, we have the rule here already saying the distance. So the distance will be x and y. What is x? Oh, what? Okay, x will be the speed. What is y? Y will be the time. And what are we doing? We multiply the speed and time. So this will work perfect. Who can tell us the answer here? I think the answer should be the next. No, they didn't give me that. But who can tell us what will be the answer here? Chevy will be, speed will be 105. Am I right? 105, because the fact. Because here, distance will take x and y. What is x? X is speed. And what is y? Oh, y is 21. It's here. So y will be 21. Okay. Let's see how we get 105 Chevy distance 21. Yeah. So it will be 105, and the speed, again, the speed is 105 and the time is also given. So distance, I think in physics is correct. Distance is always what? Speed times time. All right? Speed times time. Yeah. Yeah, so this will be again. So this is all, I would say this is one example of a prologue. That's it. You always have to have the facts. From the fact, you build your rules. And the rules can be as many, and the facts can be as many as we want. Then now the question will be either your query or your goal. Here they use the term query, but also we can say our goal. So this is a tracing. Here we say a trace is a built-in structure that displays the instantiation at each step. Remember, instantiation in logic means what? Binding the variables. That is binding the variables like the x, what value. It's not like object-oriented programming. Instantiation means creating an object from a class. Again, here is binding. I'll use the term assign, but giving each variable the correct value, binding them. And that's what we call here. So the trace model of execution, we have 4 events. When we call, exit, redo, or when there's a fail. So beginning of attempt to satisfy a goal will be the calling. Exit is when the goal has been satisfied. We finish, we have to exit. Or to redo when we backtrack occurs. Or the last option, it didn't work, it fails. And this is also an example, I would say the same concept. We have all the facts, and now we have our rule, then we're doing the tracing. So the first fact, we have Jake like chocolate, Jake like apricots, Darcy like etc. etc. So let's go to the next, the tracing. Here we have X like Jake, and we say the comma is N. So S like Jake, N, Daisy like X. And now we want to trace this. So first thing we call is, again, we go by Jake likes. That's Jake called. And the second, we have Jake and chocolate, like chocolate. Then we have Daisy, and then the rest, all the, again, options are variable down. So here they say we are going to exit. Who can tell us why we are going to exit at Jake like chocolate? Because we satisfy the goal. Let's say Jake like, we don't know. Here they say underscore 0. Well, Jake like 0, nothing there. But the second one, if we look at our fact, yes, it's true. We accomplished. Now the terms are here. Exit means what? When we satisfy our goal. So they say exit when the goal has been satisfied, we exit. Call, begin, attempt. Now, if we didn't, like the first one didn't meet, there's no more, of course, if we go through and there's nothing, we didn't achieve anything, of course, same thing, we stop, nothing will happen. But here, luckily, the fact this is true for us, so we exit. Exit is when the goal is satisfied, and we exit. Then we call Daisy and chocolate also is good. I think Daisy is chocolate. No, Daisy is not chocolate. That's why it's fail. So that's why they write here fail, because Daisy don't have no chocolate. Actual chocolate is only Jake. And let's see this one. They say this one is exit. Jake apricots. Yeah, so that's not true. Yeah. Exit, so it's true. So this exit, this can also exit, because Jake also have an apricot. Let's see, this one was a Daisy. Yeah, so Daisy have an apricot. So again, the whole thing here I'm trying to say is, based on this, we can understand what is a call. Exit means, again, when we satisfy the goal. If the goal didn't satisfy, then we have failed. That's if we go through all the items and no satisfy, we have failed. Or here they say when a goal fails. So that's why we have the exit, call, etc. Redo also is down there because we don't have that. So if no question, then let's go through the concept of list in logic. So I would say it's almost the same as functional programming. So we can see the example. We have a list of, but you have to be in square brackets. We have a list of apple, prune, grape, etc. Here we can check if list is empty or not. We can check which one is the head and tail. So head is X and tail is Y. We have it on. So this is empty list, same as functional. This, we put a vertical line. We divide the head section of the list and the tail section. So wait for a few seconds if any question. So let's keep going. So I think the exams, let's put some coding inside because I think this will be more better for us. The functional programming, where the code we put, to be honest, maybe less than 50% of the class were able to get the code. And that was a little bit trick because those who get the code, they did very good job. The thing is that when you write in the functional programming, you have to be careful with the parentheses. So somebody have over 10 parentheses is kind of, you can't even read that thing. So I think functional programming code, you are writing the algorithm. Logic is better. So maybe our next test, we're going to have a 2 or 3 code. Actually, I will make it the same format as, so those who didn't do good in functional, you have to do good in logic. Because logic is very straight. I mean, you get the rules, you get the facts, and they give you, so you just tell us if it's fail, exit, or true or false. So the coding is very straightforward. It's like writing SQL, select statement. You just have to know the format. But there's no algorithm. You're just doing something to get something based on some criteria. Okay, so same thing, we have append. Also in this concept, logic also, we can use append to join an item to a list, or append function is built-in function also. And then next we have some deficiencies of Prolog. The first one they told us the resolution order control. So here they say in the pure logic programming environment, the order of attempted matches, we cannot determine it. It's non-deterministic, and all matches will be attempted concurrently. So it's kind of and also the closed wall assumption, the only knowledge is what you have. So you have your facts and your rule, that's it. So kind of, again, as we said, there's no algorithm based on whatever facts you have and your rules. So those are the limitations. We can't go beyond. So a very good example would be, I prefer using like data mining or machine learning algorithm to build a model to diagnose a patient of disease A than to get an expert to take the rules from in and build an expert system to diagnose disease A. Because when you have the data will, the modeler will learn a lot from the data based on the training. Only if the training data set is balanced. A balance means we have 50-50. You get the disease or doesn't have the disease, so that the algorithm will learn both sides. Otherwise, we are going to have something called overfitting. Overfitting means you have 90% to learn, only 10% they don't have it, so it will be difficult. But again, why expert system may have the same closed word assumption, because whatever the doctor told you, that's it. So if the doctor forgets something, well, you don't. But if you are doing, you build it based on, let's say, 10,000 patients, well, they have so many characteristics, so the system will be more better than. So those are the disadvantages in so as we said, logic programming is used for in the expert system, relational data, but the common is the expert system I know of. Natural language processor also, we can use maybe this book was published a little bit older, but today, natural language processing, actually we have the Python package for that. It's called NLPK or something. So again, but Prolog also can be used for that. Now, this is what I posted. That's the end of the book. And I put a tutorial there because, as you can see, the textbook, if you read the textbook, you will see what I'm trying to say here. It doesn't go detail on the Prolog, just to give and as we all know already, I don't want to repeat this no more. This course is not a programming language course, so we cannot study Prolog everything here. But I just post this tutorial that if you are interested, go to this website. There are so many, also YouTube, there are so many videos around. So we see above link as annotated links to tutorials for again. And also I have one example here, which I want. Oh yeah, we have time. Wow, today we did good job. So again, this example is already done here. So hopefully you went through already. You should have these slides. Construct a truth table using the condition given to us, P implies to Q, inner parentheses, then implies to R, then we close the parenthesis, then imply to S. Then the second, write a following statement in a first order predicate. So the first one is very straightforward because what we have to do first of all, we have to count how many variables we have. P, Q, R, S. Wow, this is 4 variables. That means we have 16 combinations. Then after that, I will do the inner first because I have to get the result here as 1 value. Then I will do it with this one. Then I'll get the result here as 1 value. Then I'll do it with this one. So when you get this, the 16 combinations, 0, 0, 0, 0, 0, 1, then you start to do the implication with P and Q first. So the result is here. I think you should have it. So you can see all the P. So here we are using TF. T same as 1, F 0.
This is just mathematics, right?
Yeah, the same concept. So we have the PQRS, possible 16 combination. So what we do first, we do the P price to Q because it's inner. It's inner. Then after that, we do PQ to R because it's the next inner. Then we do what? PQR to S, which will be the final result. So if you understand the implication truth table, that's it. That's it. So we know that implication truth table, the only time we get false is when what? P is so I'll take this 2 here.
P is false.
Yeah, if I'm using this 2 here, let's say PQ, you say somewhere, yeah, so this will be false. You say P is true, this is false, so this is false. Then apart from that, everything is true. So if it's false, true, you still get true. So false, true, you get true. So the only thing I'll say is that learn the rules, the truth tables. Yeah. So Tuesday we'll see a test like this. A question like a question like this. So the next question I think is more easy. Write the following statement in first order predicate. Remember, it will be only the predicate and the argument parameter. So if it is raining or snowing, so we have or. So that's disjunction. And N will be conjunction. So if it is raining or snowing, then will be the implication. So that's all we have to know. If, or, then, they don't have N, but also, so the next question is N. If it's freezing N, there is a precipitation, then, so you have if, you have N, you have then. So you may see a question like this also, hopefully in the next week test also. So if no question here, we can see the result here. You can see where we say or, we use the symbol here. When we say and, when we say then, we use the implication. So everything. So this will be a first order predicate. So wait for a few seconds if it's okay. Okay, so we're almost done. And that's, yeah.
Do you like represent the weighting like P or you have to like write it out?
You mean the variable names? No, it can be, it can be any name.
Yeah, I'm saying like, do you have to represent it like with P or Q or?
Oh no, it depends. It's up to you. Yeah. So that's a good question. For example, here, the question here they ask, if you like, you can say, okay, you have to make the instruction. I'll say P is raining, Q is then you use PQ. Yeah. It's up to you. I say some textbook, especially in discrete mathematics, they do that. So instead of writing rain or snowing, I'll write P or Q. P is raining, Q. Yeah, you can do that too. If you did that in discrete mathematics, then you can do it here too. That's fine. As far as you specify what you are doing, that's fine. So that will be the end of chapter 16. As I said earlier, you can see the book. The book doesn't talk too much on this material. But I have another slide here. Now, I would say it's up to you. I would say do it. It's up to you. I will see if I will post that slide. Same thing like the functional programming language. I post a special slide over 100 slides just for your own review if you want to. So that slides have a lot of user-defined, a lot of functions, example functions, so that we get used to the functions. So the same thing apply here. I have another slide. I haven't posted it yet, but since we have time, let me see if I can get that slide open. It's more than, it's 85 slides. So these slides talk about logic program, more detail. This is beginning of the, so for example, you can see that I have this definition twice. I left it, what the book said, I left it, and I bring this one to that slide. So this is another textbook for, it's called Programming Paradigm by some author. So the same concept by different textbooks. So this is example two I posted in the book, because the book didn't give us much example. But the only thing I want to say here is go to the logic. Here, there's more examples than there. So they even teach us how we do execution in logic. So here it gives you the rules, then we do some query, give you the result. I'm not going to go through, again, it's the same thing we went through, but here we have more examples. So I'll post this slide, just look at it. Or if you have any question Tuesday, we can discuss it. Now we have only 10 minutes, but luckily we finished chapter 16. So the next chapter on Tuesday will be chapter 12. We finish 15, 16. We finish 5 to 8, 8 or 9, 9. So we go to 12, then 13, 11, wherever we reach, we stop. So let me wait a few seconds, see if any question first. Okay, so I'm going to stop my recording.